Waiting to buy a home? The Churchill Mortgage team says now is a great time to buy. Waiting could be a costly mistake because when rates drop, new home buyers will flood the market, driving up home prices. Go to churchillmortgage.com for your free analysis and see how home values can outpace rates to help you build wealth over time faster. This is a paid advertisement. NMLS ID 1591. NMLSconsumeraccess.org. Equal housing lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Right now, new and current customers can get any phone for free at US Cellular, so you can connect with all your family members this holiday season. You can even call your aunt who always makes you talk to your cousin, who's a dog. Or, maybe just send her a festive text. Get the gift of connection at US Cellular. Get any phone free today. US Cellular, built for us. Terms apply. Visit uscellular.com for details.
We value human connection with fewer distractions. US Cellular, built for us. Visit your US Cellular authorized agent, Cellular Advantage, located at 918 South Locust Street in Glenwood.
Hello, thanks for joining us. This is Space Nuts, where we talk astronomy, space science. We can solve some of your pet problems. We can do all sorts of things. As long as you're not sending them up in a Sputnik-like rocket or anything like that, we might have some advice for your pets, but not today. We've got plenty on. We're going to talk about a new discovery by the James Webb Space Telescope. It seems to have analysed the atmosphere of an exoplanet, and what they found was astonishing. We're also going to look at the true shape of our galaxy, and it's not for soccer fans. And with the World Cup on, I thought we would have been there, but no, not at all. And we're going to answer questions about Jodrell Bank and, surprise, surprise, dark matter and black holes. All coming up on the very next edition, this one, of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to tell all is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Fancy seeing you here.
Indeed, yes. Yeah. It's a strange place for me to be in my office with
Space
all
Nuts.
My bits and bobs over my shoulders. There's my Space Nuts tote bag. And
Very
my
good.
Space Nuts. I'm wearing my Space Nuts T-shirt.
On the. Where's your mug?
Yeah.
Where's your mug?
It's over there. Oh, hang on.
There it is.
It's
just creeping into view.
There.
Yes.
Yeah. Got my mug.
Yeah.
Oh, there it is. I'll leave it in shot with all those 4th and 5th place trophies behind me as well. Yeah.
There's a few. The hole-in-ones there.
Several
of them. Yeah.
3. Yeah. All very different. How have you been?
Busy.
I'm sure.
Yes. We have a VIP visit from senior members of the European Southern Observatory who are touring Australia next week. And
they finally found us.
They found us, and I'm looking after them for the week, or at least accompanying them, as we visit a lot of major astronomical centres in Australia, starting with Perth and then going on to Canberra. Sadly missing out Melbourne and Adelaide. We couldn't fit those in, nor Brisbane, but winding up in Sydney.
So they don't get to see the great Melbourne telescope?
They don't, no, they don't. But that's because it's called GMT, and GMT is also the Giant Magellan Telescope, which is one of their competitors, so they wouldn't want to do that. No, so we're in the final stages of arranging all that, and at least I hope we are. They all wind up at our house, actually, Andrew. They'll be in this very room in exactly a week tomorrow for dinner. Wow. Work that one out.
We should get them all on for an episode. That would be a spanking good time.
I think their schedule is just too crowded already, but it's a great idea.
I wouldn't impose, Fred. I know how busy you are, so maybe some other time.
Maybe some other time.
Yes. All right, let's get down to today's topics. And first up, another revelation by the James Webb Space Telescope. And it's gone back to a planet it sort of looked at very early on after it was made operative or operational. And we've made some amazing discoveries, you and me personally. Because we got to use it.
We've read it.
Yeah.
You're right. It's WASP 39b, which, if I remember rightly, we saw a spectrum of very early on in the piece, which had traces of water vapor in it. And shortly after that, the first unequivocal detection of carbon dioxide in the atmosphere of an exoplanet, and I think that was also WASP-39b. The latest results, though, are, they were pretty impressive, what we've heard so far, but the ones that we're seeing now are really quite staggering, because the Webb, using its infrared equipment in a way that lets you investigate the atmosphere of this planet as it passes in front of its parent star. And so what you can do is you can look at the spectrum of the star on its own, and then look at the spectrum of the star with the planet in front of it. And that means that some of the starlight's being filtered through the atmosphere of the planet. And you can actually tell the difference between the two. And the difference between the two is the signature of the compounds and elements within the atmosphere of the planet. And so there's just this wealth of information that has turned up, including direct confirmation of the carbon dioxide. The water shows up as well. I'm looking for the list because I've got a list somewhere here of all the new things that have discovered in this, and I can't find it. But I do know that one of the things that has excited people is the fact that they've detected sulfur dioxide. And that surprised the scientists. There's a nice quote here from Diana Powell, who's a NASA Hubble Fellow and an astronomer at the Center for Astrophysics at Smithsonian Center for Astrophysics. Sorry, mumbling here.
Yeah, you're right.
She says, this surprising detection of sulfur dioxide finally confirms that photochemistry shapes the climate of hot Saturns, because I should have mentioned that WASP-39b is about Saturn size, but it's hotter and it's also fluffier. It's puffed up.
It's all right. I was going to ask you.
Oh, good. Okay. Thank you.
I am useful,
No, look, you're my life belt, Andrew, because when I garble on about things and forget to mention the most important ingredient, that we're talking about a star, not a planet, or something like that, you're there to catch the loose ball, which is great. But that surprising detection is something that's, as she said, it highlights photochemistry. She goes on to say, Earth's climate is also shaped by photochemistry. So our planet is more in common with hot Saturns than we previously knew. It's something that's got of course, because if you've got chemistry like this that's being affected by the sunlight, that's what photochemistry means. You've got light actually affecting the chemical reactions. Then it sort of opens up a whole possible range of things that might be going on in the atmosphere of planets like this, where you could perhaps get some really interesting and highly suggestive molecules being formed. The other things that have been discovered include spectrum of potassium. So there's an element. There's lots of evidence of water. There's carbon monoxide. That's a new one too, as well as the carbon dioxide that
explains the runaway greenhouse effect.
Yep. Well, there you go. Sulfur dioxide, as I've mentioned, carbon dioxide, again, carbon monoxide. These molecules all have multiple signatures, if I can put it that way. If you think about the barcode of a spectrum, its different imprints come from different compounds and elements, but they're often repeated in certain ways. So the sodium as well is present, which is probably less of a surprise. But water, carbon dioxide, carbon monoxide, and this sulfur dioxide are perhaps the really interesting molecules that have now been found in WASP-39b. And there's I guess, as I said, the excitement is that you've got photochemistry going on. But I think what is also exciting is that as the Webb hones its techniques, it means that we're going to be even more sensitive to the components of the atmospheres of objects like this. And I'm sure it's looking at other planets around other stars, which are not hot Saturns, and will find much more. In fact, I think the group who've done this work at Harvard Smithsonian Center for Astrophysics, they are looking to the day when they might observe the atmospheres of more Earth-like planets. And they've highlighted the TRAPPIST-1 system, which, if I remember rightly, has got, is it 7 planets around it? We've talked about TRAPPIST before.
Yeah.
It might be 4. I can't remember whether it's 4 or 7. But these are rocky planets. And so they too will probably have atmospheres. And you can use this same technique to probe the atmospheres of these planets. It's actually a bit more difficult because the atmospheres are almost certainly thinner than the atmosphere of a hot Saturn.
But it's exciting, isn't it? The prospect is there for us to learn so much. I mean, wasn't that long ago we didn't even know about exoplanets. We just assumed they're probably out there.
Probably there, that's right.
Now we've discovered over 5,000, and there's another 4,000 to catalogue. And, the list will just keep growing, I imagine.
I think that's right, yeah. There's actually another lovely quote from another of the scientists, this time at the University of California, somebody called Natalia Batala, who says, "We observed the exoplanet with multiple instruments that together provide a broad swathe of the infrared spectrum and a panoply of chemical fingerprints inaccessible until JWST. And data like these are a game changer," which I think is absolutely right. I don't think that's an exaggeration. It's one of the things that JWST was built for, the Webb Telescope, to look at the atmospheres of exoplanets, but it's clearly stonking home with a great deal of new discoveries when we're still only in the first year of, within the first year of observations.
Yes, absolutely. And WASP-39b, it's a strange planet. It is very hot, 1,600 degrees Fahrenheit.
Yep.
Mainly a hydrogen atmosphere, but all that other stuff that we were just talking about. It's 8 times closer to its host star than Mercury is to our sun.
That's right.
And it's got the mass of Saturn, but the size of Jupiter.
Yeah. And
that's just weird.
It's very weird. It's 700 light years away as well, which is, not close by in terms of what you can do with these things. So it's a very weird place. And I think you could categorize it as being not a very nice place to visit, really.
No, probably not very habitable at all.
No.
But it's great that they've revisited something that they started out with and been able to collate even more data. And as you said, being able to hone in on some rocky planets in that TRAPPIST sector will be very exciting because with that many rocky planets, the potential is there to find something extraordinary that'd be well worth talking about and investigating further. And obviously we've been looking at the TRAPPIST planets for a long time because they've been popping up in science fiction shows as potential worlds for habitation going forward. And, if we're still around in 1 billion years, we probably will have to find somewhere else to live because our sun will get too bright for us before it goes red giant on us. But, maybe the TRAPPIST zone will be worth investigating. But who knows? I mean, the more we investigate, the more we're going to find. And it's only a matter of time, Fred, before we find an Earth-sized planet that's not unlike our own. It's got to be out there.
In the Goldilocks zone of a normal star. Yes, that's right. That's certainly there are some candidates for that, but we don't know with enough certainty yet to be able to say there's an Earth 2.0 out there.
No, they haven't found one yet, but they keep talking about these super Earths, which are rocky planets that are, much bigger than our own. We couldn't live on those. The gravity would kill us. So, we've got to find a candidate that's as close to ours as it can be. And then we've got to figure out how to get there if we ever need to. And that's an even bigger problem.
That's the tricky bit.
If it's ever solvable.
Well, you could if you could build a powerful enough spacecraft and accelerate it to nearly the speed of light.
Yes.
Then you're talking about hundreds of years rather than hundreds of thousands of years, which you'd need if you use standard chemical rockets. But it is, this pesky speed of light thing.
Well, you'd then have to take a couple of approaches to transport, intergenerational.
Yep, that's right.
Approach. So, or cryogenics, or frozen embryos, or so, who knows? With robots doing all the work.
Sounds idyllic.
To activate us when we land. Could be any of those things.
Yeah, indeed.
But but that's a fascinating find by James Webb, and one that's well worth reading up if you want to chase up the paper. I'm sure it's been listed somewhere. I'm just trying to find it. Harvard Smithsonian Center for Astrophysics.
Is
that right?
Yes, indeed it is.
There you go. All right. There'll be more to report on that and other planets that become the focus of attention of James Webb, and we'll be certainly bringing that to you when they reveal more information. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Preparing for what comes next is a big part of becoming an adult. So, if your teenager says they want to join the military, they're preparing for a real challenge. Visit todaysmilitary.com, because their success tomorrow begins with your support today.
3, 2, 1.
Space Nuts.
Now, Fred, we go from one study to another, and this one has revealed the shape of our galaxy. And this includes not only the stars, but all the junk around it. So everything. So what's it shaped like?
Football, basically.
And not the round football.
Not a soccer
Some
ball.
people call soccer football.
Yeah, they do. Oh, yeah. Everybody in the UK.
Well, most people who play the game, except Australians, call it football. We call it soccer here because we've got 4 codes of football, which is very confusing.
I'm still confused about that. Anyway, the idea of a halo of stars sort of surrounding the galaxy, stars and other objects, I have to say, goes back a long, long way to when scientists were first studying the geography of our galaxy. We've got the basic idea that it's a disk, and you get that just by looking at the Milky Way itself, because it's a bright region of many, many stars, many billions of stars, which are concentrated into a reasonably small line on the sky. So that tells you that we're embedded in this disk of stars and gas and dust, and in particular, they're young stars. But then, and I can't remember, I think a scientist called Walter Baade, as it was anglicized to, during about the time of the Second World War, I think he did a lot of work on the idea that there is a much less dense, perhaps more tenuous cloud of stars in which the disk is embedded, this halo. And Baade showed that they are old stars. In fact, he called them population 2 to compare them with population 1, which are stars more or less like the sun, ones with the same sort of amount of chemical elements in it. The halo stars are this population which are thought to be much older. More recent work suggests that the halo is something that galaxies collect over time, because it's where the debris of smaller galaxies that have been swallowed up by the big ones, where they wind up. And we, in the RAVE survey that I was involved with a decade or so ago, we certainly saw evidence of streams of stars that had, they were all moving in the same direction. And the likelihood is that they were members of a galaxy that's been gobbled up by our own galaxy and found themselves in the halo. So the natural way that we've always thought of the halo is basically as, if not a sphere, a kind of flattened sphere. So what you might call a spheroid, something that's, flatter at its poles than it is around its equator because it's rotating. But this new work has shown that, oh, dear me, no, there's more to it than that. So basically they've used several major data sets that have been collected recently. And the first one is perhaps the most important, and that's the Gaia spacecraft data. So Gaia, which was launched, actually, it's nearly 10 years ago that Gaia was launched. It's astonishing because it still seems like a very new spacecraft to me. It was launched in 2013. What it's done is it measured really accurate positions in the sky of stars. So not just in our own galaxy, they've been able to measure the exact positions on the sky of stars in for example, the Magellanic Clouds, the nearby dwarf galaxies. And because you can measure positions so precisely, you can actually detect the motion of these stars sort of across your line of sight. So Gaia has turned out to be brilliant at telling us about the motions of objects and also telling us indirectly about the distances of objects. So you can make a three-dimensional plot. And that's been compiled with another survey of stars, this one conducted on the ground at a telescope called the MMT, the Multiple Mirror Telescope, because it was, when it was built, I think it had 7 mirrors, a bit like the Giant Magellan Telescope will have, all focusing to a common point. It's on Mount Graham in Arizona. And I think it now has a single mirror, but it's still called the MMT. So they've gathered huge numbers of observations of halo stars that are actually basically too faint for Gaia to see, because Gaia's only got a small telescope on board, but what it can do with brightish objects is remarkable. But you need ground-based observations to look at the fainter ones. And they've put all of these data into this model, and basically they've looked at the way the stars are distributed. And indeed, what they get is not a sphere. They get this football shape that I mentioned before, which is sort of confirmed by other work. For example, if you have build a computer model of how you expect a galaxy to form and how you expect its halo to form, you end up with a football. And so this works really well, that you've got a football-shaped halo. And actually the research, the modeling suggests that it formed when a dwarf galaxy kind of clouted our galaxy, probably 7 to 10 billion years ago. And well, the scientists are so sure that this happened that they've given this poor deceased dwarf galaxy a name, which is called the Gaia sausage Enceladus, because the Gaia refers to that spacecraft. Sausage is kind of what it looks like when you plot the Gaia data. I've heard people talk about the Gaia sausage before, but Enceladus, of course, the mythological person, giant who's buried under a mountain. So they call it that because this dwarf galaxy was buried in the Milky Way. So that's the best theory for the origin of our halo. At least one big galaxy collision, and it all ties in very nicely together. That we've got this essentially stretched out sphere of stars around the galaxy. And I think the other thing it plays into, and I'm sure you're waiting for me to finally get to this, Andrew, is the dark matter halo, because we think that all galaxies have a halo of dark matter in which they're embedded, and that's why they don't fall to bits because of their spin. And so the new results fit in well with what we know about the dark matter halo, and that probably means that the dark matter halo is also football-shaped, which is really quite remarkable.
Yeah. Does this suggest that our galaxy is somewhat unique, or would this be more common, given that you talk about a collision that created this scenario?
Yeah, we commonly see evidence in other galaxies for exactly this process taking place. There's a lovely set of images made actually by an amateur astronomer who's a very capable astrophotographer. I hope he'll forgive me because I can't pull the name of his observatory to mind yet. Anyway, it shows exactly this. It shows a galaxy edge on At least one of them does, and some of the other images have similar things. A galaxy kind of edge on with streams of stars, all perpendicular to the edge on disk of the galaxy. And so what you're seeing there is this process taking place, the formation of a halo by something smaller being swallowed up by it. It's called tidal disruption. That's the formal name of this process, because it's the tidal effect of our galaxy, the big galaxy on the small one, that stretches it out into a string of stars. It's a kind of gentle version of spaghettification, Andrew, the same thing that occurs when you get too near a black hole, which we probably will be doing in a few minutes.
Because someone's asking a question about black holes. Yes, sorry. Completely, I thought, hang on a minute, what have I missed?
Does he know something I don't know?
No. Fair enough. Because we can't see our galaxy from the outside. We're right in it, and we have to kind of work out the shape of it through other means. And I mean, we can look at other galaxies and that gives us a clue. But going forward, does this revelation give us something to work with to maybe solve other problems or issues? Or
I think it does. So you're absolutely right there, Andrew, about the fact that we're embedded in the galaxy, which makes it really hard. And to sort of map the halo is even harder than mapping the disk, because in the disk you've got clouds of cold hydrogen, which can be picked up by radio telescopes and are not obscured by dust, and you can actually map them very accurately. This was done back in the 1950s by Jan Oort in the Netherlands and others, who first demonstrated that our galaxy has spiral arms. But the halo doesn't have any of that hydrogen. It's just this colossal aggregation of stars, which we think are more dense towards the middle. Very little to get a handle on to map it. And that's why it's taken so long to figure out that, it's a football. I think the technique that's being used for this, as well as some of the conclusions, particularly about the dark matter halo, will definitely have implications for future research. I'm sure.
Okay. We're learning a lot today, Fred.
We're also learning that my neighbour seems to be, I think he's mowing his grass, which might be what you can hear in the background there.
I can't hear anything.
Oh, that's very good, very good.
Well, that's probably more because my wife thinks I'm going deaf, but
no,
there could be another reason I don't hear much.
It could be, yeah. It's not marital deafness, is it? That sort of deafness.
That's a good name for it.
The yes dear one sort of thing.
Selective deafness. That's what it is. Yes,
that's right.
I'll be deaf for the next 5 minutes, but then I'll be able to hear again later. Yeah. All right. No, that's a great revelation. And if you want to read about it, you can go to the phys.org website and find the story, The Tilt of Our Stars. It's all there. This is Space Nuts. Andrew Dunkley here. Fred Watson over there somewhere.
Roger, you're loud and clear here also.
Space Nuts with Andrew Dunkley and Professor Fred Watson.
What a nice voice.
Yes, it is lovely.
If you listen to Astronomy Daily, you might have recognised it.
Oh, is that who it is?
That's our AI reporter, Hallie.
Hallie, yeah. Good on her.
Hallie, yes.
Yeah, she sounds lovely.
She has a moment. She can be a bit feisty.
Does she suffer from marital deafness or anything similar?
She's not married.
No.
But she keeps telling me all about these guys that try to date her, one named Hal, and I warned her off.
Yeah, that's a good idea. Keep away from him.
Anyway, they've decided they just want to be friends.
Mm-hmm. Well.
Mm. Anyway, we might hear from her from time to time. We're going to hear from some people now who have questions for us, Fred. And if I just get my list, we're going to try and bump off 3 questions. This first one has I love this question mainly because of the preamble.
Yeah.
So this is Carl.
Hi, Andrew and Fred. Carl from the UK here, Ripon, North Yorkshire. Just wanted to say thank you for all you do. Me and my dad, Brian, listen to all your content. We have the Space Nut mugs and T-shirts, which we use with pride. My dad and I have just visited Jodrell Bank for a day, and we absolutely loved it. Question for Fred. Can you tell us any stories you have been involved with Jodrell Bank? All the best, guys. Carl and his dad.
Oh, that's lovely. Thank you, Carl, and hi, Brian, and thanks for supporting Space Nuts and getting all the bits and bobs that the mug and get a tote bag. There's one there. I'll send you mine. The T-shirts. Yeah, that's great. Good on you. Oh, that's, we're chuffed, aren't we, Fred?
We are. Yeah, it's fantastic to hear about all that. And I hope Carl's merchandise fits in better than mine fits me, which is why I don't often wear it.
That's one thing I'll remind people. If you get a polo shirt, they're in American sizes, which are much bigger than the Australian sizes. So if you're normally an extra large, order a large.
Yeah.
Because I ordered an extra large and, have a look.
No, that looks normal compared with mine. You could get both you and me in mine, Andrew, because it's an XXL, I think.
Oh, okay.
Yeah, so anyway,
wow,
that's all right. Marnie always says, it looks as though you're wearing your dad's shirt. So actually,
an important safety tip.
Carl could give it to his dad, if it's then it would be wearing. No, never mind. Anyway, my connection with Jodrell Bank, I'm sure Carl will be surprised to hear this, and I'm almost ashamed to say it on Space Nuts, but for all, Jodrell Bank has been built into my soul since 1957, when the Lovell telescope was dedicated. It was an almost single-handed achievement by a gentleman by the name of Sir Bernard Lovell, who was one of the great scientists of the era in the time when I was growing up. Everybody respected Sir Bernard Lovell because he managed to persuade a motor car company to fund his telescope, and did all kinds of really novel things, like picking up Sputnik 1 before anybody else did.
Wow.
Really quite remarkable stuff, because that was 1957 as well. But having said all that, the nearest I've got to Jodrell Bank is being able to see the dish from the M6 when you're doing 70 miles an hour or some extraordinary speed, 100 kilometres an hour, and trying to look through the trees that line the M6 to see whether the dish of the Jodrell Bank telescope is visible or not. Because sometimes it's not. It's only visible when it's kind of looking at the horizon, so the arc of the dish sticks up above the trees. But every time I go down the M6, I risk life and limb by trying to find the telescopes. You've got to know exactly where to look. However, that distance is probably coming to an end next year. Because one of Marnie's tours, we're planning to take in the Jodrell Bank telescope, assuming the Director General lets us. But since he used to work alongside me here in Australia, Phil Diamond, maybe I can, pull in a few mates rates or something like that.
You never know.
But the thing about Jodrell Bank, so it's not far from Manchester. It's not that far from Ripon, where Carl and his dad are either. Ripon's lovely, by the way. It's a gorgeous place, and I'll mention one other astronomical connection that it has in a minute. But what I was going to say was Jodrell Bank is also now the home of the headquarters of the Square Kilometre Array Observatory. So that institution is a three-nation facility. It's got its low-frequency telescopes in Western Australia, or it will have when they're built. Its mid-frequency telescopes are on the High Karoo in South Africa. Their two are being built, but the headquarters is at Jodrell Bank. And so what you tend to get when you're mixed up with SKAO, the observatory, is photographs that show the South African telescopes as an artist's impression there under a beautiful clear blue sky. They show the Australian telescopes as an artist's impression under a beautiful clear Australian sky. And they show the Jodrell Bank dish under a clear blue sky, which I don't think has ever happened there, that near to Manchester. I'm sure it's a Photoshop job, and I keep telling people, you can't show that. That's not, nobody think
realistic.
Britain.
That's false information.
False information. Just very briefly, the other connection that astronomy has with Ripon, where Carl and his dad live, is that the tomb of Charles Piazzi Smythe is there, who you probably won't recognise, but he was, I think he was the second, he might have been the third Astronomer Royal for Scotland, and the first person who discovered that you need to be on a mountaintop to do good astronomy. He actually went and observed on Teide, which is a volcanic mountain in Tenerife in the Canary Islands and realized that how stunning the viewing is from a mountaintop. But towards the end of his life, he got a bit hooked on the magical powers of pyramids. He went slightly wonky. And so his headstone is not actually a headstone, it's a pyramid, quite a large pyramid. It's in one of the churchyards in Ripon, which I have visited rather than not having visited. So, Carl, I'm sure you know about that, but if you don't, go and have a look.
Yeah, that's worth a weekend visit.
Yeah, it is. It is.
It'll take you 5 minutes.
Yeah, and Ripon's a lovely spot anyway, so worth going.
All right. Lovely to hear from you, Carl and Brian. And yes, short story is Fred's never been to Jodrell Bank.
But I love the place. I love it dearly.
I haven't either, but I've got a much better excuse than you.
You've got a better excuse than me. Yeah, you have. Absolutely. Yeah.
All right. Let's move on to our next question from Leon.
Hello, Fred and Andrew. Leon from Canberra here. Love your show. Forgive me for another dark matter question. If we know about dark matter because of its gravitational effects, does it or could it, dark matter, clump together to form its own stars and galaxies?
Wow, that is a really fascinating idea, Leon. Thank you. What do you reckon, Fred?
Well, dark matter stars, yeah, I think people have talked about that possibility, but not ones that would, unlike normal matter, and most of it's hydrogen, when that collapses under its own gravity, the temperature goes up and the hydrogen fuses to helium, and you've got a star because it's radiating the excess energy. With a dark matter star, maybe what you just end up with is a very intense concentration of these dark matter particles, whatever they are. Now, I'm not, of course, an expert on the details of dark matter, because I'm not an expert on the details of anything except a few things that I was involved with back in the day. But I think it's likely that we'll find that there are more than one species of dark matter particle. There might be multiple ones, in the same way as we've got multiple particles in the normal world, the baryonic world, as it's called, where we can see the quarks and the electrons and the photons, all these sort of particles that we recognize. Maybe dark matter has a similar suite of particles which might be able to react with each other in curious ways that we don't really know about. So there might be dark matter stars that do something other than shine. I don't know what it would be. But to cut to the chase, to the bit that we are certain of, yes, dark matter does clump into things the size of galaxies, because that's how we think the galaxies in our universe formed in the early stages of the universe. You've got dark matter which clumps together. It acts as a kind of gravitational source which pulls in the hydrogen. The hydrogen forms the stars, and the galaxies are formed out of that aggregation of stars. So what you end up with is a visible galaxy inside a big ball of dark matter, football-shaped, of course.
Yes.
In fact, one of my colleagues, I think it was Matthew Collis who made this comment, described galaxies as beacons of light on hills of dark matter. When you look at the gravitational distribution, that's what they look like, the dark matter hills on which these bright objects, the galaxies themselves, sit, the bit that we can see. So it does clump together.
Yes, but whether or not it does anything other than hold galaxies together,
we don't know.
We don't know.
No, we don't.
No. So the answer is for Leon, maybe.
Yeah. Well, it's better than no, which was the answer to Carl's question.
Yeah, very true. All right. Thank you, Leon. Hope all is well in Canberra. Sorry you have to live with politicians. Now, let's...
They're okay. I was with them the day before yesterday at the Prime Minister's Science Prizes. They're all right.
Yes. One of my former employees from my previous life is now a politician. So I used to be his boss, and now he's...
yes.
Yeah, now he's a member of Parliament.
He is. In fact, he's a minister, actually. I heard him on the radio.
He is a minister.
I heard him on the radio yesterday.
Yes,
when I was
indeed.
driving back from Canberra.
Yes. He's pretty good at doing radio interviews as politician.
He would be.
The funny thing is, he used to interview politicians and get really frustrated when they wouldn't give him an answer, and now he's learned how to do it.
Yeah. Yep.
He's a good egg. Got a lot of time for him, which is good because we worked together for many years. All right, let's go to our final question for today, and this one is about black holes. Surprise, surprise.
Andrew and Fred, this is Bill Bogan from Ann Arbor, Michigan, with a question about black holes, like everybody else. So I was playing with the equation for escape velocity, square root of 2gr, and I thought, well, is it possible to have a dense object like a neutron star of a certain size where the escape velocity would be greater than the speed of light? So you wouldn't have to have a singularity to have a black hole. And I come up with like a neutron star that's 40 kilometers in radius would be essentially a black hole. So what am I doing wrong? Thanks.
All right, Bill. I don't know if you heard the clunking in the background. That was Fred working with his Cuisenaire.
Actually,
try and figure this one out.
You're not far off what I was trying to do there, Andrew, because I'm conscious that we're on YouTube, and so I shouldn't just disappear. And about 10 minutes ago, my pen fell off the table, and I wanted to write that Bill was from Ann Arbor. The only thing I could find to write with was the lead of a pencil that happens to be on my desk. So just the lead. So that's what I was using to write. It came out of this, which is a clutch pencil that doesn't work anymore. So it fell out.
Oh, right.
So,
yeah.
Anyway, it says, it could be Ann Arbor, I think, that says there.
That's a beautiful part of the world, is it not?
I believe so. It's not somewhere I've been. It shares with Jodrell Bank the honour of not having been visited by Fred Watson. But yeah, we should run a tour there sometime. I think it is a beautiful part of the world.
Yeah.
But a great question, and I think you basically need an expert in general relativity to give the proper answer. But I think that the answer is that for extremely intense gravitational fields like this, the normal formula for an escape velocity simply doesn't work, because you've got to have relativistic components in it. And the kind of thing I'm thinking of is just to give you an example of the way this sort of thing tends to work. If you imagine two objects approaching one another, and each one of them is traveling at 2/3 of the speed of light, or thereabouts, or let's say nearly the speed of light, does that mean that their closing speed is nearly twice the speed of light? Which can't be, because you can't do anything faster than the speed of light. And the answer is no, because there's a relativistic term that comes in there, which usually looks like something like 1 minus v over c squared, where c is the speed of light itself. And I suspect, I've had a quick look online, come up with a paper called A Relativistic Escape Velocity Maximum of Light Speed, which does indeed have relativistic terms like that in the formula. So the light speed formula doesn't work when you've got very intense gravitational fields that come in. There will be terms that almost certainly look like 1 over c squared somewhere in it, because that's the way it always seems to come up when you do these analyses. So that's the best of my knowledge at the moment, Bill. It's a great question. And if I was a specialist in, relativity, I'd probably be able to give you a more cogent answer than that. But I think that's the line. I think that's the bottom line as to why you're not getting the right answer.
Okay. Bill, if you want to look up what Fred looked up, you need, because it's about black holes, you need to look on the dark web. Dear, oh dear.
Yeah. I don't know whether I'd advise anybody to go and look at the dark web.
No, I wouldn't go near the dark web.
I wouldn't want to go near it either.
It's a scary place.
It must be, and probably followed quickly by a knock on the door from some agency.
The Australian Federal Police.
That's right, yeah.
Indeed. All right, Bill. Not sure we could hit the nail on the head for you there. But
it wasn't the nail on the head. It was kind of hitting it relativistically on the head.
Yes, indeed. And now I did quickly, while you were doing all that really easy stuff, I looked up Ann Arbor, founded in 1824. I found this interesting, Fred. Ann Arbor was named after the wives of the village's founders, whose wives were both named Anne.
Oh, wonderful.
And the arbor bit refers to a stand of bur oak trees.
Yes, lovely.
Yeah.
I thought it.
And I do know the PGA Tour plays in that district every year. I'm pretty sure the golf goes there once a year. But yeah, beautiful part of the world. Lots of water. All right, Bill, thank you so much. Hope you're well, and thanks for sending in your question that we couldn't do anything with much.
I thought I did a reasonable job on that, Andrew.
I think you did, yes. Your access to the dark web just surprises me greatly.
Would surprise me too.
Just a reminder too, if you would like to send us some questions, we've got a whole bunch at the moment which we're working our way through. You just need to go to our website, spacenuts.io or spacenutspodcast.com, and click on the button on the right-hand side that says send us your voice message. You can do it that way, or you can hit the AMA tab. I'm doing this right now. And you just go from there, where you can start recording. Press the start recording button, and don't forget to tell us who you are and where you're from. Important safety tip, make sure you've got a device with a microphone, because otherwise we'll just get blankness, which accounts for nearly half our questions. No, it doesn't happen.
It accounts for most of the answers.
Yep. And if you want to send us a text question, you do that on the AMA tab as well. And while you're on the website, why not go to the Space Nuts shop, because that's what Carl and Brian did, and they got their shirts and they got their Maseratis and they got all in the Space Nuts shop. Just click on shop and you'll find it there. Lots of goodies available there. And if you're on the internet doing space stuff, go to our Space Nuts Facebook page, because we've got a big following there, or you can join the Space Nuts podcast group on Facebook. That's a user-generated page where you can all chat to each other and compare your astronomical photos or ask questions and get all sorts of inane answers, and some very good answers too. But there are a few jokesters in there that I have seen from time to time. It's always good fun to see what people are talking about on the Space Nuts podcast group on Facebook. Fred, we are done for another day. Thank you so much.
It's a pleasure, Andrew. It's been a delight not being able to answer people's questions.
Yes, and that's, and after all these years, we are maintaining our standards.
Yes, we are. Yeah, that's right. Mediocre to the end.
Yes. We only strive to be adequate here at Space Nuts. Haven't said that for a very long time. I can hear a curlew in the background.
You can, yeah. There's a curlew there.
There's a curlew at the door.
Yes, there is. There was somebody grabbing a pair of binoculars to look at it.
To check out the curlew. Yeah. Let's listen to it. There it is. Yeah. Yeah, there was one that lived in a tree across the road where I was growing up, and the blasted thing thought that doing that at 6 o'clock in the morning was really good.
They do. They love it. Yeah.
Oh, so I've never been fond of them, but they have a very, very unusual call. Fred, until next time, thank you, and we'll talk to you soon.
Sounds great. Look forward to it, Andrew. Take care.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio, who did absolutely nothing at all today, as per usual. From me, Andrew Dunkley, until next time, we'll see you on Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.